In this lab, we are going to learn about the problems associated with the salt-contaminated drilling fluids and the procedures used for the drilling fluid treatment when salt contamination happens during drilling. When we are making drilling fluids with optimal rheological properties, we prefer to use high-yield clays. Here, the yield of clay in fresh water is defined as the number of barrels of 15 centipores drilling fluid obtained from 1 ton of dry clay. The yield of clay depends on the swelling capacity of the clays. Hence, it is important for us to understand the factors associated with the swelling of clays. Clays can be seen as a stack of thin sheets of molecules, with each sheet having an edge surface and a face surface. The edge of the sheet may carry charges from the breaking of bonds, and the charges may be positive or negative depending on the pH. On the other hand, the face of the sheets will always carry negative charges. Some types of clays, namely smectites, which are commonly known as bentonite, and mixed-layer illite/smectites, swell in polar solvents such as water. This means that the layers of intercrystalline sheets will start to move apart. How much they swell will be influenced by factors like the type of the cations in between the layers, the charge of the layers, and the salinity of the fluid. The type of cation in the exchangeable sites is the dominating factor when it comes to the swelling behavior of clays. A monovalent cation, like sodium, can associate with a single charge-deficient area. As you can see in the figure, this means there is little interaction between the sheets and they are nearly free to separate when dispersed in water. A divalent cation, such as calcium, cannot effectively associate with two negative charge centers on one sheet, and thus must bind two sheets together. Even then, water can still cause swelling, and mechanical dispersion may separate a sheet, and the volume of closely associated water will be much smaller compared to the sodium system. In this figure, you can see that both calcium and sodium Montmorillonite are stacked sheets of molecules when they are in their solid forms. However, when they are dispersed in water, the separation between the calcium Montmorillonite sheets, shown in the top right, are much smaller than that of the sodium Montmorillonite sheets, shown in the bottom right. That concludes the first video of this lab. In this video, we discussed the definition of clay yield and its importance, the microscopic structure of clay, how clay swells, and what influences the swelling of clay.